It's Mrs. Mafucci, and right now, let's consider thermodynamics. Thermodynamics is the study of energy changes accompanying physical and chemical changes. Heat flow. Heat energy always flows from a warmer substance to a cooler substance. Remember, cold does not flow. Cold is just the absence of heat. It always moves from a region of high temperature to low temperature. Heat will continue to flow until both substances are at the same temperature. Let's consider endothermic reactions. An endothermic reaction occurs when a system gains or absorbs energy from the surroundings. This means that the temperature of the surroundings decreases. In an endothermic reaction, we say that the delta H, the heat of reaction, is positive. This diagram represents an endothermic reaction. Reactants plus energy goes to products. Notice that the reactants have a lower potential energy than the products. The reactants must absorb energy from the surroundings to be converted into products. Let's consider this specific equation. Nitrogen plus oxygen plus 182.6 kilojoules produces 2 moles of nitrogen monoxide. This is an endothermic reaction. The heat input is the amount of energy that must be absorbed by the nitrogen and oxygen, or in the diagram called A plus B, in order to be converted into C, or nitrogen monoxide. Delta H is the heat input. Notice that it's the interval that goes between the reactants and the products. The delta H for this reaction is positive 182.6 kilojoules of heat energy. It takes 182.6 kilojoules to convert reactants into products. And where does that energy come from? It comes from the surroundings. Let's consider an endothermic reaction as it pertains to the concept of conservation of energy. Remember, energy cannot be created or destroyed. This represents a system and surroundings before a reaction occurs. In an endothermic reaction, the system absorbs energy from the surroundings. And after the reaction, it looks like this. The energy of the system has increased, while the energy of the surroundings has decreased, but the total energy is the same. Reactants plus energy absorbed from the surroundings yields product. Let's now consider an exothermic reaction. An exothermic reaction is one in which the system loses or releases energy to the surroundings. When the energy is lost to the surroundings, the temperature of the surroundings increases. We say that the delta H, the heat of reaction of an exothermic reaction, is negative. Notice the potential energy diagram for this exothermic reaction. Reactants go to products plus energy. Notice that the reactants have a higher potential energy than the products. The reactants must lose energy to the surroundings in order to be converted into products. Let's consider the reaction between nitrogen and hydrogen to produce ammonia. In this reaction, 1 mole of nitrogen will react with 3 moles of hydrogen to produce 2 moles of ammonia and 91.8 kilojoules of heat energy. That's the heat output. The heat output is the amount of energy that must be released in order for A plus B, in other words, nitrogen plus hydrogen, to be converted into C, which in this example is ammonia. The heat output is delta H, and for this reaction, delta H is equal to negative 91.8 kilojoules of heat. Remember, in an exothermic reaction, delta H is negative. In this example, we see that in an exothermic reaction, the system has lost energy to the surroundings before the reaction, after the reaction. In this example, the energy of the reactants and products decreases while the energy of the surroundings increases, but the total energy does not change. In an exothermic reaction, reactants are converted into products and energy is released to the surroundings. Calorimetry is an experimental procedure that measures the energy transferred during a physical or chemical change. A calorimeter is used to measure the heat absorbed or released by a system by measuring the temperature change of a given mass of water. By measuring the change in temperature of the water, we can determine whether the water has absorbed energy or lost energy. If the temperature of the water has gone up, water has experienced an endothermic reaction, which means that the system has experienced an exothermic reaction. The heat exchange in a calorimeter should be between the system and water only. Heat should not be lost to the air outside the container. That's why we use a styrofoam cup in our class, because styrofoam is a good insulator. In a calorimetric experiment, the heat lost by the system is equal to the heat gained by the water. And the heat gained by the system is equal to the heat lost by the water. we can use the following formula to determine the amount of heat gained or lost by the water in the calorimeter. Delta H equals mCp delta T, where delta H is the change in heat energy, or the heat of reaction. M is the mass. Cp is the specific heat, and delta T is the change in temperature. Specific heat, Cp, has to do with the relationship between energy transfer and change in temperature. We know that different materials heat up at different rates. In this picture, we see that gold heats up about 7 times faster than aluminum. The tendency of a substance to gain or lose heat energy and change temperature is related to its specific heat. A substance with a large specific heat does not readily change temperature. So consider this figure. If the same amount of heat energy is applied to the same amount of sand and water, which would experience the greatest increase in temperature? The specific heat of sand, 0.84. The specific heat of water, 4.184. Since sand has a lower specific heat, it will absorb energy and increase in temperature more readily than water. Specific heat is the amount of energy needed to raise 1 gram of a substance 1 Celsius degree.